Mount Saint Helens in Washington state is one of the most well-monitored volcanoes on the planet.
On May 18th in 1980, it exploded in a volcanic display never before witnessed in modern times.
Mount Saint Helens has a history of violent eruptions. Back in 1980, for instance, the volcano erupted with such might that the memories of that disaster are still fresh in the minds of those who lived through it. But now it appears that history is about to repeat itself. Recent seismic activity beneath the mountain has prompted urgent warnings from geological experts. NASA says that the magma is recharging beneath Mount Saint Helens after 44 years of eruption. This could lead to unpredictable and far-reaching consequences. As we stand on the precipice of understanding these recent changes, the lessons from past eruptions, and what might be at stake if this geological giant stirs once again. Let's get started. Recent seismic activity. Since February 1st, 2024, Mount Saint Helens has experienced an uptick in seismic activity, with approximately 350 earthquakes recorded by the Pacific Northwest Seismic Network, while over 95% of these earthquakes are less than magnitude 1, making them too subtle to be felt at the surface. The increase in events per week, peaking at 38 in early June, has raised eyebrows among experts. The largest earthquake recorded during this period was a magnitude 2 event on May 31, 2024. Seismic activity is occurring at a median depth of about 3.5 miles or 5.7 kilometers below sea level, well beneath the volcano's crater floor. While some geologists argue that these fluctuations are within the realm of normal background seismicity, others are starting to ring alarm bells. So, is there another disaster of epic proportions in the making? Well, there's no simple answer to it. Let's just get all the facts on the table first. Historically, short-term increases in earthquake activity at Mount Saint Helens are not uncommon and are often interpreted as part of the volcano's natural seismic behavior. The periods of elevated seismicity observed in 2023 and 2024 are the most significant since the last eruption in 2008. Similar increases occurred in the late 1980s and 90s, but these did not lead to eruptions. While this might suggest that the volcano is simply following its usual pattern, there are notable differences this time. Seismicity levels have reached peaks that are reminiscent of the largest short-term increases seen before previous eruptions. Naturally, some experts are now questioning whether this could be a precursor to something bigger. The ongoing seismic events are believed to be related to pressurization within Mount Saint Helens' magma transport system, specifically due to magma recharge. This is when new magma enters the upper reservoirs beneath the volcano. This process can increase stress, leading to earthquakes. While recharge events are not inherently dangerous and have been observed at Mount Saint Helens and other volcanoes, the current rate of seismicity could indicate that the volcano is stirring. Naturally, there is a growing concern among some researchers who fear that the current sequence of earthquakes could be signaling a larger, more forceful event brewing beneath the surface. This concern has persisted for decades. NASA monitors Mount Saint Helens using a combination of satellite and ground-based technologies. For example, the Advanced Spaceborne Thermal Emission and Reflection Radiometer, or ASTER, onboard NASA's Terra satellite, provides crucial data on volcanic activity. ASTER's capabilities allow it to capture detailed images of the mountain's surface, including thermal and visible spectra, which are essential for monitoring changes in temperature, ash emissions, and surface shifts. This technology helps track volcanic activity and its potential risks, particularly with the growth of lava domes and the occurrence of steam and ash plumes over the years. NASA also collaborates with other institutions, including the U.S. Geological Survey or USGS and various universities, to collect data and model the volcano's behavior. This partnership is vital for the continuous analysis of volcanic hazards, which supports early warning systems and enhances disaster preparedness efforts. The importance of these monitoring efforts is immense, as volcanic eruptions like the one in 1980 can have significant environmental, social, and economic impacts. By providing timely data on volcanic activity, NASA and its partners help mitigate risks to local communities and infrastructure. This ongoing surveillance is crucial for issuing warnings about potential eruptions or other dangerous volcanic events. This is not hyperbolic. The volcano has a persistently violent history. A history of natural disasters. Known as Lawet Latla to the Cowlitz people and Luwit or Luwala Clough to the Klickitat, Mount Saint Helens is nestled in Skamania County, Washington, approximately 52 miles northeast of Portland, Oregon, and 98 miles south of Seattle. Surrounded by the towering peaks of the Cascade Range, including its sibling Mount Adams to the east and Mount Rainier to the north, Mount Saint Helens exemplifies the breathtaking beauty and volatile power of nature. Nearby, Mount Hood in Oregon lies 60 miles to the southeast. Geologically young compared to its volcanic peers, Mount Saint Helens formed within the last 40,000 years, with its now infamous summit cone beginning to rise about 2,200 years ago. Before its devastating eruption in 1980, it stood as the fifth highest peak in Washington, its symmetrical cone often likened to Japan's Mount Fuji, earning it the moniker Fuji-san of America. With a base spanning 6 miles and a cone width of 4 miles near the tree line, its icy summit, crowned by 11 glaciers, was a striking feature of the landscape. However, the eruption dramatically reshaped the mountain, leaving behind a crater that now hosts the geologically youthful Crater Glacier. The surrounding area boasts a web of natural waterways fed by the region's abundant rainfall, averaging 140 inches annually. Streams originating from Mount Saint Helens feed 3 major river systems: the Toutle River to the north and northwest, the Kalama River to the west, and the Lewis River to the south and east. These rivers support ecosystems and human needs alike, with the Lewis River also serving as a source of hydroelectric power through its dammed reservoirs. Beneath Mount Saint Helens lie 2 magma chambers, the upper chamber, located 3 to 7 miles beneath the surface, and the deeper one between 7 and 25 miles deep, house molten rock that feeds the volcano's activity. The lower chamber is thought to connect with nearby volcanic systems, like Mount Adams and the Indian Heaven volcanic field, highlighting the interconnectedness of volcanic structures in this region. The volcano's life story began in the Pleistocene epoch, around 40,000 years ago. But it wasn't until the year 1800 that the first oral and written records documented Mount Saint Helens's violent history. This period began with an explosive eruption, producing widespread ashfall over the Pacific Northwest and beyond. A lava flow followed, culminating in the creation of a dome named Goat Rocks on the volcano's northeastern flank. This dome became a prominent feature and remained until the 1980 eruption obliterated it. Smaller eruptions continued sporadically between 1831 and 1857, with a significant event in 1842. Notably, the 1831 eruption's ashfall may have contributed to unusual atmospheric phenomena, such as a bluish-green sun observed in Virginia, famously interpreted by Nat Turner as an apocalyptic signal. But the worst was yet to come. The volcano was only stirring up for a big showdown. The next big thing happened more than a century later. The disastrous 1980 eruption. After remaining dormant for 123 years, Mount Saint Helens reawakened in March 1980, initiating a series of seismic and volcanic events that captivated and alarmed geologists and the public alike. The first signs of activity came on March 15th, when a series of small earthquakes suggested magma movement beneath the volcano. The seismic activity escalated on March 20th, with a magnitude 4.2 earthquake striking beneath the north flank. Over the following days, a relentless earthquake swarm unfolded, peaking on March 25th and the following day with a significant magnitude 5.1 event. In just 2 days, 174 shocks with magnitudes of 2.6 or greater were recorded. Sounds eerily similar, does it not? On March 27th, the volcano erupted for the first time in over a century. Steam explosively interacted with groundwater heated by ascending magma, blasting apart rock within the summit crater and creating a new 250-foot wide crater. An ash column rose 7,000 feet into the air, while a network of fractures, stretching 16,000 feet across the summit, further signaled the mountain's instability. In the days that followed, additional explosions sent ash plumes 10,000 to 11,000 feet high, with the volcanic fallout traveling as far as Spokane, Washington, over 285 miles away. The eruption on March 29th introduced new dynamics as a second crater formed, and blue flames, likely from burning volcanic gases, were observed flickering above both craters. Lightning generated by static electricity within the ash clouds illuminated the dramatic scene, with bolts reaching lengths of up to 2 miles. By the end of March, the volcano had produced 93 distinct outbursts in a single day, and harmonic tremors, which are continuous, earthquake-like vibrations caused by magma movement, emerged as a critical warning sign on the 1st of April. Washington's Governor Dixie Lee Ray declared a state of emergency on the 3rd of April, marking the beginning of stringent safety measures, including the establishment of a red zone. April brought more ominous developments. The crater, now 1,700 feet wide, had deepened to 500 feet by April 7th. Meanwhile, geologists observed the north flank of the volcano bulging outward at an alarming rate, displacing the surface by 270 feet and growing up to 6 feet daily. By mid-May, this bulge extended over 400 feet outward. It grew due to the intrusion of magma into the mountain's interior. This created a cryptodome, which is a hidden, pressurized magma body, forcing the summit to sag into a graben, or sunken block. This deformation increased the volcano's overall volume. By late April, geologists identified the bulge's instability as the greatest immediate threat, warning that its collapse could trigger a catastrophic eruption. Steam-driven eruptions resumed on May 7th, but visible volcanic activity subsided by May 16th. Public interest waned, and the reduced activity led some to underestimate the potential danger. On May 17th, officials permitted 50 carloads of property owners to retrieve belongings within the danger zone, with plans for another trip on May 18th. Additionally, many loggers, who would normally work in the area, were absent due to the weekend. The worst was yet to come. As the volcano silently prepared for its climactic event, the bulge had extended nearly 500 feet outward. Over 10,000 earthquakes had rattled the mountain in the preceding weeks, concentrating just below the bulge. The magma intrusion continued heating the groundwater system, causing recurrent steam explosions. By the eve of May 18th, Mount Saint Helens stood on the brink of one of the most significant volcanic eruptions in modern U.S. history. That fateful day, Mount Saint Helens appeared to follow the same routine as it had over the previous month. Observations from USGS volcanologist David A. Johnston, stationed approximately 6 miles or 10 kilometers north of the volcano, showed no signs of abnormal activity. Temperatures, sulfur dioxide emissions, and the movement of the growing bulge remained within expected levels, offering no indication that an explosive eruption was imminent. By 6 in the morning, Johnston had not detected any unusual seismic activity, and everything seemed calm. However, that tranquility would soon be shattered. At 8:32 a.m., a magnitude 5.1 earthquake, centered directly beneath the volcano's north flank, triggered a catastrophic chain of events. The shock of this earthquake set off the massive landslide that would go on to become the largest subaerial landslide in recorded history. Occurring just 7 to 20 seconds after the earthquake, the slide swept across the northern side of the volcano, reaching a speed of 110 to 155 miles per hour, or 177 to 249 kilometers per hour. It raced down the slopes of the volcano and traveled across the western arm of Spirit Lake. Some parts of the landslide hit a ridge 1,150 feet, or 350 meters high, about 6 miles or 10 kilometers away, but the majority of the debris moved downstream, filling the North Fork Toutle River's valley with an avalanche of debris up to 600 feet, or 180 meters deep. The slide covered an area of approximately 24 square miles or 62 square kilometers, with a total volume of debris around 0.7 cubic miles or 2.9 square kilometers. Remarkably, a series of rapid photographs taken by Gary Rosenquist, who was camping 11 miles away, helped scientists reconstruct the movement of the landslide. His camp, along with the photographs, survived because the eruption's force was deflected by the local topography, stopping the blast a mile short of his location. The scale of the devastation was monumental. A massive rubble deposit, 17 miles or 27 kilometers long, was created, with a thickness averaging 150 feet or 46 meters. The thickest portions of the slide reached up to 1 mile below Spirit Lake. The tremendous force of the landslide temporarily displaced the waters of Spirit Lake, sending a massive wave as high as 600 feet or 180 meters over the ridge to the north of the lake. When the waters returned, they carried thousands of uprooted trees, which had been ripped from their roots by the explosion of superheated gases and ash. These trees, many of which were intact with their roots, were sent crashing back into the lake. The surface level of Spirit Lake was raised by around 200 feet or 61 meters, and floating mats of logs remained in the lake for years, moving with the wind and gradually sinking as the trees became waterlogged. Over the decades that followed, these trees began to petrify in the mineral-rich anaerobic waters of the lake. The eruption also unleashed a lateral blast, an explosive pyroclastic flow, as the magma beneath the volcano's neck was exposed to significantly lower pressure. The partially molten rock, still gas-charged, along with high-pressure steam, detonated in a violent explosion shortly after the landslide was triggered. The explosion, which erupted from the trailing part of the landslide, sent hot volcanic gases, ash, pumice, and pulverized old rock surging outward. This lateral blast moved at speeds of about 220 miles per hour initially, accelerating rapidly to 670 miles per hour, potentially even exceeding the speed of sound for a brief moment. The pyroclastic flow, which was made up of extremely hot gases and ash, spread rapidly over the landscape, devastating an area approximately 23 miles across by 19 miles long. It resulted in the destruction of around 230 square miles of forest, with the intense heat of the flow scorching trees far beyond the blowdown zone. This lateral blast was over in about 30 seconds, but the cloud of ash and gases continued to expand and radiate outwards for another minute, causing devastation over an even wider area. The eruption also caused a secondary explosion as the superheated flow materials interacted with the waters of Spirit Lake and the North Fork Toutle River. The water flashed into steam, adding to the blast's force and sending shockwaves that were heard as far away as British Columbia, Montana, Idaho, and Northern California. Interestingly, some areas closer to the volcano, like Portland, Oregon, did not hear the eruption at all, forming what became known as the quiet zone. This anomaly has an explanation. When a large explosion occurs, sound waves propagate in all directions. However, atmospheric conditions, such as temperature gradients, wind speed, and air density, can bend or refract these sound waves. This phenomenon, known as acoustic shadowing, occurs when sound waves are directed upward into the atmosphere and refracted back down only at greater distances from the source, kind of like how light bends when entering into a medium of a different density. Overall, the force of the eruption was visible for miles. The effects of this massive release of energy can be broken into several concentric zones. The innermost zone, known as the direct blast zone or tree removal zone, extended about 8 miles from the volcano. Within this area, the eruption's violent force obliterated nearly everything in its path, from natural features to man-made structures. The energy released in this blast was equivalent to 24 megatons of TNT, making it one of the most powerful eruptions ever recorded. The blast was so intense that the surrounding topography provided no resistance. Nothing could deflect the ferocious flow of material, and the ground was left barren, as if stripped of all life. The channelized blast zone, extending out to 19 miles, demonstrated the blast's ability to be funneled and channeled by the surrounding geography. While the destruction in this area was severe, it was not as total as in the innermost zone. The force of the eruption leveled trees and flattened structures, yet the landscape exhibited fascinating evidence of the forces at play. In areas where the blast was channeled by valleys and ridges, large trees were uprooted or snapped off at the base and lined up in parallel patterns. This zone, also referred to as the tree-down zone, displayed a stark visual imprint of the eruption's direction. In open areas where the blast hit directly, the landscape was scourged, with trees broken short and vegetation, including topsoil, stripped away, making recovery a slow and arduous process. However, in areas where the blast passed overhead, the ground was left relatively undisturbed, preserving the topsoil and seeds, which led to quicker revegetation. The seared zone, or standing dead zone, marked the outermost extent of the destruction. While trees remained standing, they were singed brown by the intense heat of the eruption's gases. The eruption also claimed the lives of 57 individuals, including several notable victims. Among them was volcanologist David A. Johnston, who was stationed at Coldwater 2 Observation Post, just 6 miles north of the volcano. Johnston and others, like photographer Robert Landsberg, who was within a few miles of the summit, lost their lives either from the deadly pyroclastic flows or the ash cloud that followed. Landsberg's final act, sheltering his film with his body, ensured that future generations would have a vivid visual record of the eruption's fury. Harry R. Truman, the owner of a lodge near Spirit Lake, was buried under hundreds of feet of avalanche debris. As the pyroclastic flows continued, the deposits they left behind formed an intricate pattern of overlapping sheets, tongues, and lobes that would remain visible for years. These flows, which were still at extreme temperatures of 570 to 790 degrees Fahrenheit, or 300 to 420 degrees Celsius for weeks after the eruption, continued to be active with secondary steam blast eruptions, especially around Spirit Lake and along the North Fork Toutle River. These eruptions were sporadic, with some occurring even as late as a year after the initial eruption. The ash column from the eruption was equally astonishing. It reached a staggering height of 12 miles in less than 10 minutes. The eruption was so powerful that it generated lightning, which sparked numerous forest fires. As the ash cloud continued to rise, it collapsed in parts, causing additional pyroclastic flows to surge down the volcano's flanks. These flows were filled with pumice bombs and very hot pumiceous ash, which created craters in the earth as they came into contact with water, and sent ash soaring into the sky. In total, Mount Saint Helens released 540 million tons of ash, which was carried by winds at speeds of up to 60 miles per hour, and reached cities as far as Spokane, Washington, where visibility dropped to just 10 feet. The ash clouds circled the globe, impacting places like Minnesota and Oklahoma within weeks. The eruption's massive pyroclastic flows, combined with glacier melt and mud flows, rapidly reshaped the surrounding landscape. Lahars, or volcanic mudflows, formed as glaciers melted and ash mixed with snowmelt, traveling at speeds of up to 90 miles per hour and inundating rivers and infrastructure, tearing down bridges and flooding regions. These flows continued throughout the day, culminating in the merging of debris-laden waters in the Toutle and Cowlitz rivers, causing record-breaking flood levels. This catastrophic event reshaped the environment, highlighting the destructive power of volcanic eruptions and their long-lasting impact on both the landscape and infrastructure. A large mudflow also formed at the head of the Toutle River's North Fork. By 2:30 p.m., this flow destroyed Camp Baker and wiped out 7 bridges, continuing its journey down the Cowlitz River and eventually reaching the Columbia River. The mudflow deposited around 3.9 million cubic yards of material into the river, lowering the depth by 25 feet over 4 miles, which obstructed shipping channels and caused a temporary closure, resulting in an estimated $5 million in losses for Portland's port. The eruption also displaced 65 million cubic yards of sediment, reshaping entire regions and leaving lasting environmental impacts. The eruption also ejected over 1 cubic mile of debris, altered the landscape, and devastated local wildlife, including timber and salmon populations. Ash clouds also caused severe transportation issues, closing roads and disrupting air travel for days. The ash, fine-grained and abrasive, caused mechanical failures in vehicles and short-circuited electrical transformers, leading to power outages. Washington state spent no less than $2.2 million to remove 2.4 million cubic yards of ash from highways and airports. This process took 10 weeks in Yakima alone. Ash disposal was a complex task. Many disposal sites were hastily chosen, including quarries and landfills, and some were covered with topsoil to prevent the ash from blowing away. In addition to direct economic costs, which were estimated at $1.1 billion at the time, the eruption severely impacted local industries. Unemployment in the region surged tenfold in the immediate aftermath. But the recovery began as timber salvage operations and ash removal projects ramped up. Although tourism took a severe hit, the region eventually rebounded as Mount Saint Helens became a site of renewed interest, drawing visitors eager to witness the aftermath of one of the most iconic volcanic eruptions in modern history. The U.S. Forest Service and the state of Washington opened visitor centers, providing access to the devastated area and helping to revitalize the tourism industry. However, this was not the end. Far from it. Eruptions and disasters after the 1980 catastrophe. Between May and October of 1980 alone, there were 5 additional explosive eruptions. In the years that followed, the volcano remained active, with more than 21 eruptions occurring through early 1991, and even continuing with smaller dome-building eruptions into 2008. The early months after the May 18th eruption were marked by a series of smaller but still significant events. On May 25, 1980, A relatively minor eruption sent an ash column 9 miles into the atmosphere. This eruption followed an increase in earthquake activity, and the ash was carried by erratic winds south and west, lightly dusting parts of western Washington and Oregon. In early June, Mount Saint Helens continued its unstable behavior, producing a plume of ash on June 12th that reached altitudes of 2.5 miles. By June 9th, a much stronger explosion sent ash soaring 10 miles into the sky, affecting even Portland, which had remained unscathed during previous events. In July, a series of powerful eruptions added to the mounting instability. On July 22nd, for example, a series of explosions sent an ash plume soaring 10 miles and resulted in the destruction of the dome that had formed earlier in June. These eruptions were preceded by an increase in seismic activity, shifts in gas emissions, and changes in the volcanic landscape. The event's intensity was notable, and it saw ash rise faster and higher than previously recorded. By 7:01 in the evening, the final explosion began, continuing for over 2 hours. The volcanic activity continued throughout the summer, with further eruptions recorded in August. On August 7th, a significant ash cloud rose to 8 miles, while pyroclastic flows surged through the northern breach of the volcano. A new dome began to form, marking the slow and persistent recovery of the volcano's internal activity. After a brief period of calm, activity resumed in October, with an eruption that lasted from October 16th to 18, demolishing the second dome, sending ash into the sky and generating small pyroclastic flows. In the aftermath of this explosion, a third dome began to emerge, growing steadily over the following days. By the end of the month, the third dome was already 900 feet wide and 130 feet high. From December 1980 to January 1981, the volcano experienced an episode of lava extrusion, and by 1987, the third dome had expanded to more than 3,000 feet or 910 meters in width, and 800 feet or 240 meters in height. These quieter eruptions would persist into the early 1990s, with further dome-building events recorded through 1991. The period from 2004 to 2008 marked another significant phase in Mount Saint Helens' volcanic history. Starting in October 2004, a gradual process of dome building resumed. Unlike previous eruptions, this new dome did not rise above the rim of the crater formed by the 1980 eruption. The activity continued into January 2008, with steady lava extrusion continuing to reshape the crater's interior. Throughout these decades of activity, Mount Saint Helens has undergone significant geological changes, with satellite images showing the ongoing growth of lava domes and shifts in the landscape between 1982 and 2017. So what's the worst that can happen now, or in the immediate future? Worst-case scenarios for a future eruption. While much of the volcanic activity in recent decades has been relatively contained, the possibility remains that the volcano could trigger an event of similar or even greater magnitude. Experts warn that the likelihood of a major eruption, akin to the one witnessed on May 18, 1980, cannot be ruled out. The US Geological Survey has consistently monitored Mount Saint Helens, and while the eruptions since 1980 have been relatively modest, the ongoing seismic activity and periodic increases in gas emissions suggest that the volcano still possesses the potential for significant, explosive events. In terms of worst-case predictions, experts have developed models based on the data gathered from Mount Saint Helens' previous eruptions. These models predict that a major eruption could lead to the release of vast quantities of magma and ash, creating conditions similar to those seen during the 1980 eruption. The possibility of a mega eruption at Mount Saint Helens remains a catastrophic concern. Mega eruptions, which involve the eruption of tens to hundreds of cubic kilometers of magma, are incredibly rare but highly destructive. A mega eruption would release a tremendous amount of volcanic ash and gases into the atmosphere, possibly leading to a volcanic winter, which is a dramatic cooling of Earth's climate. An eruption of this scale would have severe global consequences. Not only would it devastate the region surrounding the volcano, but the cooling of the atmosphere could cause crop failures, food shortages, and a drastic impact on global weather patterns. Pyroclastic flows, another product of explosive eruptions, are some of the most destructive forces unleashed by a volcano. These fast-moving currents of hot gas, ash, and rock can travel at speeds greater than 100 miles per hour and can reach temperatures of up to 1,000 degrees Fahrenheit. They can obliterate everything in their path, including infrastructure and human settlements. While experts caution against overly alarmist predictions, they agree that the potential for a catastrophic event at Mount Saint Helens remains. With continued monitoring, scientists aim to better predict and understand the behavior of this active volcano. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.